very good morning to everyone. So, we were discussing about the solution of spherical polar coordinate system, partial differential equations in spherical polar coordinate system by using separation of variable. And in the last class, we have seen that how to solve a two-dimensional problem. Now, we will be looking into a three-dimensional problem today, and many of the engineering applications we deal with the spherical coordinate system. For example, if you are talking about the heat transfer in a ball or in an ingot, metallic ingot, then one has to take recourse to the spherical polar coordinate system. The heat transfer problem from a sphere is very important in various engineering applications, starting from covering mechanical, aerospace, chemical engineering and other engineering disciplines. Similarly, in refinery engineering, there we have to store the oil in Horton spheres and gases and oils, etc., in the Horton spheres, petrochemical products. So, there the spherical polar coordinate system is very important for quantifying the temperature distribution and other things. So, therefore, spherical polar coordinate system, the solution of partial differential equations in spherical polar coordinate system is an integral part of any PDE's application for engineering problems. So, in the last class, we have looked into the two-dimensional problem. In today's class, we will be looking into a more generalized problem, which is nothing but a three-dimensional one. So, let us look into the example of spherical polar coordinate system. It is a three-dimensional problem, and we are assuming there is no phi symmetry. So, thus the problem formulation will be grad square u will be equal to 0. That means, if you write down in its complete form, it will be 1 over r square del r square del u del r plus 1 over r square sin theta del theta sin theta del u del theta plus 1 over r square sin square theta del square u del phi square is equal to 0. So, this is a complete problem in a three-dimensional symmetry, three-dimensional domain, and the boundary conditions are at r is equal to 0, you have u is equal to finite value. So, this is bounded, it will be assuming a finite value, and at r is equal to 1, we have u may be a constant, may be a function of theta, may be a function of phi, or may be a function of theta and phi both, and the boundary conditions on theta and phi will be evolving out of physics of the problem, as we will see later on, physics of the problem. So, they will be the physical boundary condition. Thus, let us, as we will be going ahead with the solution, we will be looking into the boundary conditions in more appropriate version. Now, we will be looking for a separation of variable type of solution. So, u r theta phi should be is equal to r of r, capital theta of theta, phi of phi. So, it will be considered to be a product of three functions. One will be function of r alone, another will be function of theta alone, the other one will be function of phi alone. Now, if I replace this in the governing equation, then it becomes theta phi d dr of r square dr plus r phi divided by sin theta d theta of sin theta d capital theta d theta plus r capital theta divided by sin square theta d square phi d phi square is equal to 0. Now, I divide both sides by r theta and phi. So, let us see what we get. What we get is that, and then I multiply it by sin square theta as well. Okay. So, sin square theta divided by r d dr of r square dr plus sin theta divided by theta d theta of sin theta d theta plus 1 over phi d square phi by d square phi d phi square. So, that will be constituting this equation. Then we will be formulating a standard eigenvalue problem in the phi direction, taking the physical boundary conditions on phi, which are nothing but the periodic boundary conditions as we have discussed earlier. So, let us write it in the in a special form, that sin square theta by r d dr, so that we can formulate a standard eigenvalue problem dr plus sin theta by theta d theta sin theta d theta is equal to minus 1 over phi d square phi d phi square, and left hand side is a function of r and theta only, the right hand side is a function of phi only. So, and they are equal, and they will be equal to some constant, and this constant has to be a negative constant in order to have a non-trivial solution. So, in order to have a non-trivial solution, we will be having a negative constant out there. Now, let us formulate the standard eigenvalue problem in the phi direction, and let us formulate the boundary conditions on phi, which are nothing but the physical boundary conditions. So, if we remember that phi is varying from minus pi to plus pi, and we will be having the periodic boundary conditions. Periodic boundary conditions are on phi are phi at pi is equal to phi at minus pi. Okay. d phi at pi will be nothing but d phi at minus pi. Okay. So, therefore, we will be having d square phi d phi square minus lambda square phi should be equal to 0. This is the eigenvalue problem. With this boundary condition, and we have seen earlier that if we have this boundary condition, let us solve this equation. So, phi is equal to this will be solution will be composed of sine functions and cosine functions. So, a m sine lambda phi, okay, let us say C 1 sine lambda phi plus C 2 cosine lambda phi. Now, phi at pi becomes C 1 sine lambda pi plus C 2 cosine lambda pi is equal to phi at minus pi C 1 minus sine pi lambda pi plus C 2 cosine lambda pi. So, minus lambda pi, cosine minus lambda pi will be same as cosine plus lambda pi. So, these two will be cancelled out. So, what you will be getting is 2 C 1 sine lambda pi is equal to 0. So, C 1 for C 1 not equal to 0, we have sine lambda pi is equal to 0. So, lambda pi is equal to m pi, there is a general solution when m runs from 1 to infinity. So, lambda m is equal to nothing but m, the natural numbers. Now, in the next, what will be utilizing the other boundary condition, that d phi at pi is equal to d phi at minus pi. So, if you use this boundary condition, so what is d phi? D phi is nothing but C 1 lambda cosine lambda phi minus C 2 lambda sine lambda phi. So, now if I utilize this boundary condition, this becomes C 1 lambda cosine lambda pi minus C 2 lambda sine lambda pi is equal to C 1 lambda cosine minus lambda pi is same as plus lambda pi, and this will be minus C 2 lambda sine minus lambda pi. So, it will be minus plus lambda pi. So, these two will be cancelled out. So, you will be having 2 C 2 lambda sine lambda pi will be equal to 0. So, therefore, for a non-trivial solution, sine lambda pi will equal to 0. So, lambda pi is equal to m pi, there is a general solution infinity, and therefore, we will be having lambda m is equal to m, which are the natural number. So, from both the boundary conditions, we are going to get lambda pi will be equal to m, where the index m runs from 1 up to infinity. Now, if we use a value of lambda to be equal to 0, then we can see that what will happen to the our eigenvalues. Okay, so d square phi d phi square will be equal to 0 for constant lambda equal to 0. So, for the case when lambda equal to 0, so you will be having phi is equal to C 1 phi plus C 2. Now, if we use the boundary condition that phi at pi is equal to phi at minus pi, then this becomes C 1 pi plus C 2 is equal to minus C 1 pi plus C 2. So, C 2 will be cancelling out. So, we will be having 2 C 1 pi equal to 0. So, C 1 will be equal to 0. So, your phi will be nothing but C 2. Okay. Now, for if you look into the other boundary condition, other boundary condition is d phi at pi is equal to d phi at minus pi, and if phi is equal to C2 is the solution, then this will be always satisfied. Is it, if phi is a constant, then this will be always satisfied. Okay. So, therefore, phi is equal to constant is also an eigen function, is also a solution and eigen function. So, therefore, we will be having now if you combine. So, now what are the eigen functions we are getting? One is the phi is equal to a constant, that is a constant, and then another will be phi is equal to, let us say, a m sin m phi plus b m cosine m phi, where the in this equation m runs from 1 to up to infinity. Now, we have two solution or two eigenvalues functional form. One is phi is constant, another is phi is equal to a m sin m phi plus b m cosine m phi. Now, m is equal to 1 to infinity, where the m are basically the natural numbers. Now, we can combine these two equation, these two solutions eigen functions into one eigen function if we run our running index m starts from 0. Let us look into what if we start counting our m from 0 instead of 1. Now, let us see what will get at phi at m equal to 0. At m is equal to 0, if I evaluate this equation, I will be getting sin 0 is 0 and b m will be a constant. So, therefore, if I take m, if I count m from 0 to infinity instead of 1 to infinity, I will be taking care of the eigen function phi is equal to constant. So, in general, I can the eigen function for phi varying part is in general phi is equal to a m sin m phi plus b m cosine m phi, where m starts from 0, 1, 2 up to infinity. So, that completes the eigenvalue problem in the phi direction. Now, we can always show that if lambda, so we have considered the constant lambda is 0, the constant negative, and if it is positive and bring it to the other side, then you will be getting a non-trivial solution. So, we can just have a look into that one. So, d square phi d phi square minus lambda square phi is equal to 0, and you know the solution of this. The solution of this will be C1 exponential lambda phi plus C2 exponential minus lambda phi. Then we write down the boundary condition phi at pi is equal to phi at minus pi. So, C1 exponential lambda pi plus C2 exponential minus lambda pi is equal to C1 exponential minus lambda pi plus C2 exponential plus lambda pi. So, this if we take it to the other side, C1 exponential lambda pi minus exponential minus lambda pi, and here it will be having C2 common exponential lambda pi minus exponential minus lambda pi. So, this will say that C1 will be is equal to C2. Okay, these two are equal and opposite. So, we will be having phi is equal to C1 common exponential lambda phi plus exponential minus lambda phi. Okay. Then we will be utilizing the other boundary condition d phi at pi is equal to d phi at minus pi. So, if you utilize this will become C1 lambda exponential lambda phi minus lambda exponential minus lambda phi evaluated at pi, and here it will be C1 lambda exponential lambda phi minus lambda exponential minus lambda phi evaluated at minus pi. And if you really put this C1 lambda exponential lambda pi minus lambda exponential minus lambda pi, and this will be C1 lambda exponential lambda pi minus lambda exponential this is minus lambda, this is minus 1 is plus, so it will be lambda pi. So, if you take minus common, so it will be the identical and same, and they will not be equal to 0. So, you will be getting C1 will be equal to 0. So, one will be getting a trivial solution. So, you will be getting ultimately landing with phi is equal to 0. So, one will be getting a trivial solution. For the non-trivial solution, we are really looking for the non-trivial solution. Therefore, phi m of phi will be nothing but a m sin m phi plus b m cosine m phi, where the index m runs from 0, 1, 2 up to infinity. So, this will take the case of constant eigenvalue as well, constant eigenfunction as well. So, we will be having the eigenfunction for m is equal to 0, it is constant. For m not equal to 0, for any other value, it will be combination of sine function and cosine function. Now, let us look into the r varying part and other parts. So, sine square theta divided by r d dr of r square dr plus sin theta divided by theta d theta of sin theta d theta is equal to minus m square, where m is from 0 to infinity. Now, we take it to the we constitute the eigenvalue problem in the theta direction maybe. So, it will become minus. Okay, so one more step, I divide by sine square theta. So, 1 by r d dr of r square dr plus 1 over sin theta d theta sin theta d theta is equal to minus m square sin square theta. So, I take it on the other side and m square sin square theta on this on this side. So, it will be 1 over r d dr of r square dr is equal to 1 over sin theta d theta sin theta d theta plus m square sin square theta is equal to minus lambda square. So, this will be equal to, this is a function of r only, this will be function of theta only, they are equal and they will be equal to some constant, and that constant may be a new constant, maybe lambda minus lambda square, and it has to be a negative constant, because in order to have a non-trivial solution. Now, we will be able to formulate the eigenvalue problem of theta direction in the theta direction. If we do that, the eigenvalue problem in the theta direction becomes d d theta sin theta d theta plus m square divided by sin theta capital theta plus lambda square sin theta capital theta is equal to 0. Now, if you remember, if you look into this equation, you can find out that this sin theta is nothing but the weight function. If you look into the standard eigenvalue problem in the form of L theta plus lambda r theta is equal to 0. So, this will be in the form of L theta plus lambda square r theta is equal to 0. It is basically w theta. W is nothing but the weight function. Okay. So, here the weight function in the spherical polar coordinate system is sin theta, and now once we get that, I divide both sides by sin theta, and let us see what we get. 1 by sin theta d d theta sin theta d theta plus m square sin square theta plus lambda square theta will be is equal to 0. So, this will be the form of the eigenvalue problem in the theta direction, and we will be looking into the solution of this, and I will be taking this up in the next class. I will stop here in this class. We will complete this problem in the next class, and then we will be looking into other problems as well. Thank you very much.